The next book is Predictive Geometry by Coxeter. It's yet another Coxeter book, this time focused on predictive geometry. And it covers all kinds of predictive geometry, but mostly the classical parts. So we see here triangles, we see here duality, of course, and it does all kinds of, it goes very deep in predictive geometry, all from a synthetic point of view until at the end it does coordinates, and it tells you how to construct coordinates. It's again, like any Coxeter book, it's extremely broad. It doesn't go deep, but it is very broad, and it tells you a lot about predictive geometry and a lot of the applications in math. So it has like combinatorics, it has coordinatization, it has connections with algebra, it has really a lot of things, but it's also a very classical book. It's not the kind of geometry that people do today. It's very much all classical ideas, classical geometry. But yeah, I think like any Coxeter book, it's really nice. It's really a beautiful book. Next, we have here Geometry of Manifolds by Nicolaescu. I'm not sure if I pronounced that well. And this is a really nice book on manifolds. So it's really first of all, the pages feel absolutely awesome. I don't know if you yeah, you can't feel it obviously, but the pages are really nice. The book is a bit more of an advanced version than Lie, so I would not take this as your first book. As you see, it starts with smooth manifolds, and then it goes immediately to the tangent bundle and tensor fields, whereas Lie is a bit more gentle. It goes to Riemannian geometry fairly quickly. It does integration on manifolds in like 20 pages, and in page 100, while Lie takes like a very, very big part of the book to get there. We see here calculus of variations on manifolds, which Lie doesn't even cover. The fundamental group, cohomology, which Lie covers very briefly, and characteristic classes, which Lie doesn't cover. And then electric equations, Dirac equations, all of which is more geared towards analysis. So it is true that the book is very geared towards both analysis and, in a sense, what you're interested in physics, while the book of Lie would be more interesting for like pure geometers, even algebraic geometers. The book is very beautifully written. It has exercise in line with the text, which is my favorite actually. I really like that format. But yeah, it's an amazing book, but definitely should not be your first book. It's fairly advanced. But yeah, I guess if you're into differential geometry, like if you really want to know more about differential geometry, I think this is the book that you want to read after Lie, or after the Lie trilogy, to get a better perspective of how things go. Here you see the name of Noether, which, I mean, and it's what you think it is. It's the Noether theorem of physics, which tells you that symmetries are conserved, that conservation laws are identical to symmetry of the Lagrangian. So yeah, these kind of things, relation with physics, are extremely beautiful and are extremely nice applications of the theory. But yeah, Lie, or let's say even an ordinary pure mathematics book, wouldn't cover them. They wouldn't care about them. So yeah, it's still a pure book, right? It's still a rigorous book. It's very rigorous. Everything is proved very rigorously, but it is very much focused, very much a focus towards what people might need for applications. Here we have two books I really like, but they're very old-fashioned books. They're probably one of the most oldest books I have. Well, I have older books. I have Euclid's Elements, obviously, that's older, but this is very, very old. This is Veblen and Young, and there's volume 1, and there's volume 2. And Veblen, you see the paper is already It's already quite old. So the font already also gives like this old vibe, and really these are, I think, the most authoritative volumes on projective geometry. And it goes really deep into what I say is classical projective geometry, meaning that this book was written. I'm not sure when this book was written. Let me see if I can find it. I think this book was written in about 1920s. Yeah, it doesn't say it, and this was before Grothendieck basically revolutionized projective geometry. So it's very classical, and there is not even a notion of what would go on later in it. So this is really a very old view. Don't expect a modern view of things. Probably don't even expect people to talk about abstract algebra too much or linear algebra too much. It's very old-fashioned, and that's exactly what I like. I like the old-fashioned projective geometry way more than the modern version, which is very much more powerful. I don't say it's not powerful. It's very powerful, and it proves many things. And it is an active field of research, but I just don't like the vibe of it. This is basically, here we see an entire chapter on non-Euclidean geometry, which is basically why I bought the book. Especially chapter 2. The part 2 is very interesting because it is on Cayley-Klein geometries, which is the one that I'm really interested in. And it is one of the books that does it really extensively. As you see, this volume 2, even volume 2 is like over 500 pages on very beautiful projective geometry. So this is a really deep set of books, all of which is now subsumed in a very abstract theory, sadly. And I don't think many people even know what's in this book anymore. It makes me feel sad to open these books because I feel it's all like, in a sense, forgotten knowledge. I'm not saying the knowledge doesn't exist anymore, but it's very much abstracted. And I feel if you abstract geometry, you kind of lose the spirit a little bit. Here we have a very nice book, Integral Transforms and Their Applications by Debnat and Bata. Debnat is a very good writer on function analysis. There's two writers, Debnat and Mikuzinski, who have written quite a few books and also quite a few books together. And I really, really like every single one of their books. It has a really beautiful perspective on things, on function analysis. They're always a bit non-standard. I mean, with non-standard in this sense, I mean not quite the ordinary. I don't mean non-standard analysis, but they're always a bit weird, and that's really what I like because they offer a very unique perspective. Here we have a book, a very thick book, based on integral transforms, all about integral transforms. Obviously, I think Mirror will agree with me that the most interesting integral transform is a Fourier transform. So a lot of time is based on the Fourier transform. And look at the list of topics on the Fourier transform. It has, I think, a thing that you don't really see in an ordinary pure text. Like it has the Shannon sampling theorem. I don't think I've seen that in a pure text before. I've seen it in a signal processing text. The Gibbs phenomenon, which he basically treats very nicely. We see cosine and sine transforms. We see application of Fourier transform in mathematical statistics. So as you see, like Debnat, he has a really niche view on things, which I really like. And you can see that in his choice of topics. We then get to the Laplace transform. What else? We have fractional calculus, which is like derivatives, but like the 1/2 derivative or a pith derivative of a function. Very nice, very nice. The other transform are the Henkel transform, Mellin transform, the Hilbert transform. What else? Z transforms, Legendre transforms, Jacobi and Gegenbauer transforms, Laguerre transform, Hermite transforms, Radon transforms, and wavelets. So all lots of transforms you see. The book, I think, like any DevNet book, is very beautiful, very beautifully constructed, very beautiful to read. Here we see the chapter on Fourier transforms, so don't expect too much rigor in this book. Not saying that there isn't any rigor, but it's really not the focus. The focus is on how to deal with these transforms in practice, how it can be useful to us in practical situations, not so much on proving the theorem in its full rigor. It obviously has some proofs, but I think, yeah, if you're really gonna expect a proof using measure theory, rigorous measure theory, you're going to, yeah, be needing a different book. It does have, let's say, derivations instead of proofs. But yeah, very nice book, highly recommended. The next book is Electronics for Physicists, which, like it says, is a book on electronics, but for physicists. So we see the usual electronics things, and it goes on impedance, it goes on capacitors, inductors, diodes, transistors, so it has the usual things. Why is this book special? Because it really is everything that a physicist should know of electronics. I don't think it takes a very physical point of view, like it goes into the physics of things. I mean, it obviously is physics, but it doesn't go in like to the Lagrange of a circuit. I think that would be silly. But it basically tells everything what a physicist should know about electronics in order to do its own experiments. Sad to say, it's quite of a run-of-the-mill textbook. I think the only redeeming notion, or that makes it somewhat special, is the size. I think the size is quite short for a circuits book. Normally circuits books are like 3 times the size. So in that sense, if you're a physics student and you want to know about electronics, I think, and you're not interested in electronics for itself, I think this would be the book you should be going for, because it does contain everything and nothing more. Personally, though, I'm not sure I will rebuy this book if I lost it. It's not something that, it's not a book that I really am happy that I bought.